Let's talk a little bit about nutrient timing. Can you build muscle and lose fat at the same time? I've got 19 pages of notes, and I'll see you inside. So there's a few things that I want to get out of the way first just to make sure that everyone's on the same page. So the body has three main fuel sources, and these are going to be glucose, fatty acids, and ketones. The only way that we're going to get into a state of significant ketosis where we're producing a lot of ketones is if we drastically reduce our dietary carbohydrates and possibly our dietary protein to a level that the body is forced to upregulate the process of gluconeogenesis. Gluconeogenesis is the process of making new glucose out of molecules that are not already glucose. There are three main molecules we use for gluconeogenesis. The first is going to be lactate, which we will produce in the highest amount during exercise. The second molecule is glycerol, which is a structural component of triglycerides. And triglycerides are the way that we store fat in our adipose tissue and the way that fat is stored in our food. And the third thing that we'll use is going to be amino acids. Amino acids are simply what every single protein is made out of. The same way that a carbohydrate is made out of a bunch of glucose molecules, a dietary protein like a chicken breast is just made out of a bunch of amino acids. So if you want to really think about it, every gram of protein that you eat is a gram of amino acids. And now through this process of gluconeogenesis, we will actually use a specific enzyme called oxaloacetate. And this is important because this is also used in turning fatty acids into energy. The way that we use triglycerides, which are found in our adipose tissue and in our food, is by first breaking it down into its structural components. These include 3 fatty acids and 1 glycerol molecule. The fatty acids can be directly used for energy, and the glycerol can go to the liver where it can be converted into glucose, and glucose can then subsequently be used for energy. And now in order to use free fatty acids for fuel, we actually put them through a process called beta oxidation. And this has a few different steps, but the end outcome is turning a fatty acid into what's called acetyl-CoA. Once we have this acetyl-CoA, the acetyl-CoA goes through a series of processes that turns acetyl-CoA into ATP, and ATP is actually the energy that all of our cells require. With that being said, the very first step in this process requires this oxaloacetate enzyme. And now the liver is tasked with supplying the brain with all of its glucose. And if we're eating glucose, when the glucose in our bloodstream begins to lower, the liver actually has stores of glucose called glycogen that it can simply just pull from and put more glucose into the bloodstream for the brain. With that being said, if we don't have this stored glycogen, we will upregulate that process called gluconeogenesis. And this is simply just to create enough glucose to supply the metabolic demands of the brain. And when the body is tasked from either using this oxaloacetate enzyme to create glucose for the brain or to burn body fat to supply energy to the body, we are going to choose using oxaloacetate to create glucose for the brain. This means we'll have a buildup of this acetyl-CoA molecule inside of the liver. But the liver is a wonderful organ and is able to actually take these acetyl-CoA molecules and put them down a different pathway, which is the production of ketones. So as you can see, the reason that we'll actually begin to produce ketones is because we are running low on any sort of stored or ingested glucose. And one problem with this is that the brain requires glucose, so we'll begin turning other molecules into glucose. And now this is okay when we have these molecules inside of our bloodstream, but in a scenario where we don't have amino acids from ingested food, we will begin to pull amino acids out of the largest pool of amino acids inside the body, which is our muscle. And this is actually one of the reasons why I don't think a ketogenic diet would actually be great for someone who's lean. And now let me explain. Someone who has a lot more body fat and a lot more body weight will actually have a higher metabolic expenditure, meaning that their muscles and their organs actually require more energy at rest. And since these tissues can use triglycerides for fuel, we'll actually be liberating a lot more body fat. And the result is we will have a lot more free glycerol, which can be turned into glucose to supply to the brain. And no matter what your weight is, the amount of energy that the brain requires will typically be constant. So someone with a very high metabolic rate will be more likely to use glycerol to turn into glucose rather than amino acids. However, as you begin to decrease your body weight, your metabolic rate goes down. But this is the metabolic rate of your body and not your brain. the metabolic rate of your brain stays constant. But when your metabolic rate goes down, you'll have to use less triglycerides in order to fuel your entire metabolism. And this means you'll have less of these glycerol molecules available, which means you'll have an increased requirement to turn amino acids into glucose. And quite simply, we can't just choose where these amino acids are going to come from. If we're forced to do it, we will choose to pull amino acids from the muscle tissue, which means the more gluconeogenesis we have to go through, the more likely we are to lose muscle alongside body fat. And this is why being in the range of low carb but not in ketosis can be dangerous for muscle mass, because we're not low carbohydrate enough to begin to upregulate our production of ketones, which would have the downstream effect of reducing the brain's glucose requirement, meaning we'll still maintain a very high glucose requirement at the brain even though we're not eating much glucose. And this will really increase the amount of gluconeogenesis that we need to go through. So that being said, if we're completely at rest, we need about 120 to 150 grams of carbohydrates to supply the glucose-dependent tissue with fuel. And then the rest of our metabolism can be supplied through fatty acids from either stored or ingested fat. Once again, this is completely at rest, and when we're doing intense physical exercise, we have an increased demand for glucose. And the amount of glucose that we need is actually very dependent on what type of exercise we are doing. So to be broad, we'll categorize exercise into 3 different energy systems. If we're doing weight training between 1 and 10 reps, this will actually rely more on what's called the creatine phosphate system. So the muscle does have a store of ATP inside of it. And the first ATP that we will actually use before we begin creating more ATP is what is stored inside of the muscle. And now ATP is adenosine triphosphate, and all we really need to know is that there are 3 phosphate bonds attached to the end of this adenosine molecule. And we actually use the energy stored in the bond between the second and third phosphate to power almost every single cellular reaction. And this just breaks the phosphate off of ATP, giving us ATP and 1 phosphate molecule. What creatine does is it adds a phosphate back onto ADP, turning it into the high energy ATP. And this is really how, at a biochemical level, creatine will increase our energy. With that being said, the supply of creatine is very small. And now this really can only supply energy for a very small period of time, which means the longer the exercise actually lasts, the more fuel that we'll need from glucose and fatty acids. So if the only thing we're doing is strength training in a very low rep range, we may not actually use all that much glucose, which means this type of exercise won't actually raise our glucose demand all that much. And I really misspoke earlier. I would say that once we get above about 5 or 6 reps, this is when we'll start using a lot more glucose for fuel. You can really judge how much glucose you're using actually by how much an exercise session burns. And the reason I say this is because the reason that you begin to feel a burning sensation is because there are byproducts that build up as a result of not fully metabolizing glucose. And now I don't mean strain on the muscle, I mean the acidic feeling that you may get during a set that is between 15 and 20 reps, or during a very high intensity interval. The worst of these would probably be something like a 1 to 2 minute all-out sprint. So just to briefly touch on energy systems during exercise, there are 2 different energy systems, one being aerobic glycolysis and the other being anaerobic glycolysis. And the only thing you really need to remember is that aerobic glycolysis requires oxygen, but it makes a lot more energy than anaerobic glycolysis. However, anaerobic glycolysis is quicker and does not require oxygen, but it makes far less energy, which means we're going to try and supply as much of our energy from aerobic glycolysis as possible. However, the amount of energy we can create at one time is simply limited by the amount of oxygen we can supply to the muscle. And there's really not much we can do about the amount of oxygen we can get to the muscle per unit of time. But one of the adaptations to exercise is an increased VO2 max, which is simply just the amount of oxygen we can get to the muscle per unit time. So acutely, there's nothing we can do about this, but over the long term, the adaptations to exercise will actually allow us to increase our aerobic capacity. And now what's the benefit of this? In aerobic respiration, we can use both fatty acids and glucose. And it does seem that we will preferentially use fatty acids for this process, which technically means that if we increase our aerobic capacity, we'll have a greater ability to oxidize body fat, and we'll also be able to spare more glucose for the times that we actually need it. However, exercises that require a lot of energy at one time, like running a mile or doing a high intensity interval, will derive a lot of energy from anaerobic glycolysis as well, and we can only use glucose for this process. And this process produces a lot of acidic molecules. And then once we expand the duration of a session to something that is more endurance in nature, we simply have to reduce our intensity, meaning we don't need to produce as much energy per unit of time, which means more and more of our energy can actually be supplied through aerobic respiration. So something like walking or a very low intensity bike ride won't use all that much glucose, and it will use a substantially greater amount of free fatty acids or ketones for that matter. So if we take the goal of trying to build muscle and lose body fat at the same time, we're probably going to want to try and spare as much glucose as possible so we don't run the risk of losing muscle along with body fat due to this process of gluconeogenesis. So the things that we would want to be careful of and maybe refrain from if we're not eating enough dietary carbohydrates would be something like CrossFit or a very high intensity interval workout. And I know what you're thinking, if you're doing this, why don't you just eat more carbohydrates? The problem is that the more carbohydrates that we have to eat, the less likely we are to get into a state where we can actually use our body fat for fuel. And I'll talk about this more in depth in a moment, but if we're trying to lose fat and build muscle, or at least retain as much muscle as possible, it really is about having enough glucose available for the tissues that need it when they need it. So the less carbohydrates we can use in the muscle during exercise, the more carbohydrates we can store in the liver and supply to the brain. So in something like this, our cardio would likely want to be lower intensity where we'll be using mostly body fat, and we may actually benefit from doing weight training sessions in a lower rep range. This would be something between 5 and 12 reps where we'll get all of the benefits of hypertrophy training, but we may not use as much glucose as something between 12 and 30 reps. And unless you're really training for something like a mile run or a 5K, something like this may actually be detrimental if the only goal is to increase muscle mass and decrease body fat. And in no way am I telling you what you can and can't do. The only thing that I'm saying is that it would be my suggestion to someone with the goal of building muscle and losing body fat at the same time to prioritize exercise that would be, for lack of a better word, glucose sparing, which would be low intensity exercise and prioritizing lower rep range hypertrophy training. However, this is a podcast about nutrient timing, and this is going to bring us into our first nutrient, which would be carbohydrates throughout the day. So like I said, we technically don't need to ingest a single gram of carbohydrate whatsoever in order to keep the brain with all of the glucose that it needs. So the brain really has no ability to store glucose or any other macronutrient for that matter, which means the liver is responsible for keeping our blood glucose stable in order to supply the brain with all the energy it needs throughout the day and night. And when our blood glucose begins to lower, we'll use certain hormones in order to raise it. The first one that will actually kick in is created in the pancreas, and it's called glucagon. And glucagon really functions to increase the levels of free fatty acids and glucose in the bloodstream. And the way it does this is by taking the triglycerides out of body fat and to cause the liver to begin breaking down the stored glucose it has called glycogen. And now glycogen is really just a very efficient way to store a lot of glucose in the liver. And throughout the night, the body actually uses the liver glycogen to continuously supply the brain with glucose. But there really is a finite amount of glucose we can store on the body. So we store glucose in both the liver and the muscle. The muscle glycogen will typically be used during exercise, and the liver glycogen is used to keep the brain with the glucose that it needs. And now to put some numbers on this, during sleep, the energy needs of the brain alone are reduced by about 50%. But it's estimated we use about 8% of our liver glycogen every hour during sleep. So as long as we're not doing intense physical exercise and we're just doing normal day-to-day tasks, the liver glycogen will be predominantly used for the brain. and the rest of the body can use its energy from body fat. So the goal for carbohydrates is to replenish the muscle glycogen after exercise and make sure we maintain our blood glucose and liver glycogen long enough to supply the brain with all the fuel that it needs through stored glucose. In this scenario, we will not upregulate the need for gluconeogenesis, reducing the likelihood we'll have to use our muscle tissue for amino acids for gluconeogenesis, simply sparing as many amino acids as possible for the muscle. So if the liver glycogen does begin to run low and our blood glucose begins to lower, we produce a hormone in our brain called CRH. And this causes the pituitary gland to release adrenocorticotropic hormone. And finally, this will travel to the adrenal gland, causing the production of cortisol. And now cortisol is really the main hormone that's responsible for increasing the rate of amino acid breakdown from muscle tissue. Glucagon does it to a mild degree, but cortisol will do it to a much greater degree. And this does make sense because cortisol is actually produced by the brain in response to either stress or low blood glucose. And in the case of low blood glucose, this would mean that the liver has run out of glycogen and we need to increase the rate of gluconeogenesis. So cortisol will work all around the body in order to liberate as many molecules as possible to create more glucose for the brain. And unfortunately for us, this includes our biceps and our quadriceps. And now obviously working out is also a perceived stressor, and this will increase our levels of cortisol as well. And what's really interesting is that some of the studies seem to indicate that taking carbohydrates during a workout will actually decrease the cortisol response. However, this isn't something that I've tried or recommended, so I can't really give any recommendations around this. However, ingesting carbohydrates immediately after a workout certainly could do the trick. And this is where we get into the idea of actually working out in a fasted state. I'll explain in a moment, but the goal is to actually go to sleep with as much liver and muscle glycogen as possible. We would then wake up in the morning having used a little bit of our liver glycogen, but still having the muscle glycogen available for the workout. So during the workout, we will use the stored glycogen inside of the muscle, and we will continue to supply the brain with glucose through the liver glycogen. And then immediately after the workout, we would replenish all of our glycogen stores once again. And the reason that I mentioned cortisol is because cortisol is going to be one of the main reasons we'll actually begin to catabolize and break down muscle tissue during a weight loss phase. But if we can keep this cortisol response just during training and mitigate it throughout the rest of the day, we will increase our ability to retain muscle. So in terms of this nutrient timing approach, we are also going to time our workout. My suggestion is working out immediately upon waking, or as early in the morning as you can. And then immediately after working out, trying to ingest both glucose and protein. And now I don't think there's much evidence showing that there's a magical anabolic window where you can eat a bunch of Rice Krispie treats after a workout. However, I think it might be better to call it the post-workout anti-catabolic window. And the reason for this is because after a workout, you will have higher levels of cortisol and lower muscle and liver glycogen, which primes you for beginning to catabolize muscle tissue for fuel. However, after a workout, your muscle tissue will be extremely sensitive to both amino acids and glucose. And I know you may have heard before that working out will increase your glucose sensitivity, but I want to give you a reason why this will actually occur. So the act of contracting a muscle causes what's referred to as non-insulin mediated GLUT4 translocation. Now before you leave, let me just put this in simpler terms. So inside of a cell, we have what's referred to as a GLUT4 channel, but when it's sitting inside of a cell, it's not doing anything. And at rest, this GLUT4 channel will be sitting inside of the cell, so the muscle isn't uptaking any more glucose. And the function of insulin is to actually bind to the insulin receptor and cause this GLUT4 channel to travel from inside of the cell into the membrane of the cell. And when it's in the membrane, it simply just allows glucose to enter into the cell. And this process of putting it into the membrane is referred to as translocation. And at one point, it was thought that only insulin could stimulate this process. However, there's evidence showing that muscle contraction itself causes this GLUT4 translocation. Any more of these receptors that are actually expressed on the membrane, the more glucose we can uptake into the muscle tissue. And this is why I actually recommend working out and then eating a bolus of carbohydrates immediately after training. Because training will increase the amount of these glucose receptors we have available, we will take more glucose out of the bloodstream, and less of the glucose that we eat will have any opportunity to be turned into body fat. And I will talk about why we'll be more sensitive to amino acids in a moment, but I want to finish the topic of carbohydrates. So what I would recommend is trying to use the morning workout and the meal immediately after the workout not to prioritize fat loss, but rather to prioritize building as much muscle as possible and replenishing our glycogen so we do not have to resort to gluconeogenesis at any point during the day or night. I would say that this meal should contain about 70% of your daily carbohydrates, and then I would actually go low carbohydrate for the rest of the meals of the day until we get to your final meal of the day, which will contain about the other 30% of your carbohydrate. The reason you'd want to spread your carbohydrates out as much as possible if we're trying to maintain glycogen is because we actually want to intake carbohydrates in a glycogen depleted state. And if we remain lower carbohydrate during the middle portion of the day, the liver will be consistently liberating its stored glycogen for the brain. Then we could eat the rest of our carbohydrate total right before bed in order to maintain this liver glycogen throughout the entire night. And this gives us the greatest likelihood not to ever have to run low on liver glycogen, which would cause us to resort to gluconeogenesis. And now it really doesn't matter too much about the exact carbohydrates, but I do actually have a recommendation. So immediately after the workout, I would actually recommend trying to get as many of your carbohydrates, if not all of your carbohydrates, from fruit. And the reason for this is because of the speed of digestion of fruit and all of the other nutrients that are packed inside of fruit. So fruit's going to digest much more quickly than a complex carbohydrate like oatmeal or sweet potato. This will actually transiently increase our blood glucose to a much higher degree. However, it will not be as prolonged as an oatmeal or sweet potato. But because this large spike in blood glucose happens so quickly, it has two benefits. The first is that there will be much more glucose available while our muscle tissue is already glucose sensitive. It appears that the exercise-stimulated GLUT4 translocation does not actually stick around for all that long. So we would really want to try and get as much glucose as quickly as possible in the bloodstream so it can be quickly uptaken through this non-insulin mediated GLUT4 translocation. Sorry I said it again, I just really like saying that. Additionally, this large increase in blood glucose will require more insulin production, which could be very beneficial because not only is the muscle running low on glycogen, but after a workout, more of your blood flow will be diverted to whatever tissue you just were working out, which means more of the insulin will likely be diverted to that tissue. Therefore, once again, we will have greater glycogen uptake at the level of the muscle, and we will reduce the amount of insulin stimulation at other cells that we wouldn't want insulin stimulating, like the fat cells. So one benefit of fruit is simply the speed at which we can get glucose into the bloodstream and into the muscle. The other benefit of fruit are the things that it contains other than glucose. So fruit will come with an abundance of micronutrients and specifically electrolytes like potassium. And now to fully comprehend the impacts of potassium on muscle glycogen, I want to talk about just a brief bit of biochemistry. So in the body there's going to be three main compartments in which we will store water: inside the cell, surrounding the cell, or in the bloodstream. And the body will maintain an equal concentration of solutes and water in each of these three compartments. Solutes are going to be things like glucose, potassium, magnesium, calcium. Solutes are simply just things that aren't liquid, like glucose, sodium, potassium, magnesium, calcium, and other things like that. So all you really have to think about is that the more solutes in a single location, the more water we require. The main solute inside the bloodstream is going to be sodium, and the main solute inside of the cell is going to be potassium. And when there is potassium outside of the cell will actually trade the potassium for sodium. And now during exercise, more sodium will enter into the cell. And this is what actually powers all of these muscle contractions. And after exercise, the levels of sodium inside of the cell will simply just be slightly elevated above baseline. And when we eat potassium, this will actually cause more potassium to be in the bloodstream, which means we'll have more potassium in the space surrounding the cells. And the cell actually wants to get rid of this sodium, and it has a specific exchanger that will take intracellular sodium, push it into the surrounding space, and take potassium from the surrounding space and take it into the cell. And there are also other potassium channels on the cell that will simply just take in potassium. So the more potassium we ingest, the more potassium will enter into the cell. And when we have more potassium inside of the cell, more water is able to enter the cell. And now why am I telling you all this? The reason is because in order to store glucose as glycogen, every gram of glucose requires between 2.5 to 3 grams of water. And one of the reasons that after a high carbohydrate meal, your blood glucose would remain high, meaning not as much glucose is being stored as glycogen, is not necessarily because the cell can't physically store more, but there is not enough water in order to create glycogen. So this glucose will remain in the bloodstream, and if there's not enough water around, this glucose will eventually simply just be turned into body fat. And I just want you to think about that for a moment. Simply not having enough hydration could cause us to convert more of our excess energy into body fat than we would have if we had enough water and potassium. And the reason I mention potassium is because the more potassium we have, the more of the solutes will be inside of the cell, and the more water we will uptake into the cell. And this is where fruit is so beneficial, because not only does it have all of this potassium, but it has a ton of water in it. The water content of fruit is far higher than something like a potato or a grain. And now the final thing I'll mention about fruit is something that may actually surprise you, but it's the presence of fructose. Fruit will have substantially more fructose than another carbohydrate like rice or potato. And there are two real benefits to fructose. The first one is that fructose can actually use a different transporter than glucose. Fructose can be uptaken by a different transporter, meaning that less of these carbohydrates will compete with glucose for glucose uptake. And this fructose will be turned into glycogen just like glucose. So the more of these transporters that we have available, the more glycogen we can store. And now the other benefit is that it seems like the liver will actually uptake fructose much better than glucose, which means it may have a secondary benefit of further increasing our liver glycogen, which can certainly be beneficial in order to keep this glucose supply for the brain. And now if we turn to before bed, I'm actually going to prioritize a slower digesting carbohydrate. And the reason for this is because it will actually stay in our bloodstream longer, decreasing our requirement for stored glycogen. And the other reason is that a very large increase in glucose, such as ones that we would get from fruit, could actually cause what's referred to as reactive hypoglycemia. And this would simply be overproducing insulin so that we reduce our blood glucose too much. And now there's technically nothing wrong with this, but if we do this directly before bed, it will actually increase the likelihood that we will wake up as a result of low blood glucose. This is because we will actually get that small production of cortisol, which will make us feel more awake and more alert. So right before bed, we would want to look at something like potatoes or squash. With that being said, while we're on the topic of sleep, I want to mention tryptophan. And this will bring us nicely into the next topic, which is going to be protein. So tryptophan is an amino acid that we actually want inside of the brain to promote sleep. When it's in the brain, tryptophan is turned into serotonin, which will help us cope with stress. And then serotonin is eventually converted into melatonin in the presence of darkness. However, to get into the brain, tryptophan will actually compete with other amino acids, meaning that the more amino acids in our bloodstream, the less of the tryptophan will actually get into the brain. But there's a very easy trick in order to allow tryptophan almost free access to the brain. And this would be taking advantage of the meal directly after training to eat a protein source that is rich in tryptophan. And the reason for this is because directly after training, the insulin production will be increased and the amino acid uptake at the level of the muscle will be increased. Both of these will facilitate more amino acid uptake at the level of the muscle, meaning there will be less amino acids inside the bloodstream. But insulin does not stimulate the uptake of tryptophan at the level of the muscle, which means there are now less competing amino acids but more tryptophan in the bloodstream available for the brain. And it doesn't appear to matter when this increase in tryptophan into the brain occurs, as long as it occurs at some point during the day, because the tryptophan will be stored and used whenever it's needed. And this is why after training I would recommend a protein that is rich in tryptophan, such as fish, turkey, chicken, and other lean protein sources. Alright, so now that we have tryptophan in the brain and we're going to have great sleep, this takes us directly into protein. So dietary protein is the one nutrient that I want to keep constant all day long. I would want to keep a constant supply of dietary protein being consumed throughout the entire day. So after a strength training workout, protein synthesis remains elevated between 24 and 48 hours. And what's pretty interesting is that it actually appears that the peak level of protein synthesis after a workout in someone who is newer to the gym is around 48 hours after the workout. But a more experienced individual and someone who's been training longer, this peak seems to occur around 24 hours after the workout. What this really means is that protein synthesis will remain elevated for a very long period of time after a workout. And we would want to contain a continuous and high amount of amino acids through the consumption of dietary protein as often as possible. So why does protein synthesis actually elevate after a workout? Strength training will release different signaling molecules, and a lot of them actually activate a very important molecule inside of the cell called mTOR. mTOR stands for the mammalian target of rapamycin, and it is really what is regulating cell growth. And now this protein will respond to specific amino acids, insulin, and different inflammatory molecules that are produced as byproducts of exercise. There is a specific amino acid called leucine that seems to activate mTOR the most. And then in terms of exercise, it seems that byproducts such as cytokines will also stimulate this molecule to a very high degree. So exercise and the ingestion of amino acids, specifically leucine-rich amino acids, will increase the activity of mTOR. And now to understand the function of mTOR, we need to do a little bit more biochemistry. So inside the muscle cells and all of the cells inside of our body, there's a bunch of different enzymes and a bunch of different proteins, all that have different functions. However, we only activate these proteins at specific times. When the cell is at rest and we are not trying to grow and repair, a lot of the proteins and enzymes inside of our cells won't actually be functioning. And we actually need to start and go down different pathways in order to activate or inactivate certain proteins at certain periods of time in order to have specific effects. And the way that we actually tell a specific enzyme or protein to turn on or off is through a process called phosphorylation. And this is simply adding a molecule of phosphate onto an enzyme, receptor, or signaling protein, which will act as the energy that is required to cause a specific change in its function. For example, we can phosphorylate the insulin receptor and actually change the shape of the insulin receptor so insulin can no longer bind. So in the case of mTOR, these different factors that I mentioned earlier, like leucine and cytokines, can actually bind to the molecule of mTOR. And what mTOR does is it puts these phosphate molecules on different enzymes, receptors, and signaling proteins. It will actually put these phosphates on specific proteins that will bind to the DNA and cause the transcription and synthesis of proteins that are important inside the cell. And for the most part, all of these proteins are required for the process of uptaking more amino acids and having a greater rate of protein synthesis. For example, some of these proteins encode for what are called protein channels, which will go to the membrane of the cell and allow for more amino acids to enter the cell. mTOR really is going to be one of, if not the most important molecules to activate in order to kickstart the process of protein synthesis. And it's very important to know that activating mTOR will simply just signal for protein synthesis, but we also need to provide the amino acids that are going to actually be used for protein synthesis. And this is why even though stimulating mTOR after a weight training session wouldn't do anything if we don't ingest any protein. Additionally, I mentioned that leucine is a very potent stimulator of mTOR. This has actually led to the production of things such as branch-chain amino acids, which are leucine, isoleucine, and valine. In addition, it's led to the production of isolated leucine supplements. And there's nothing wrong with these supplements, but people are taking these supplements without ingesting the other essential and non-essential amino acids that we need for muscle growth. There are 21 different amino acids that the body needs for protein synthesis, and there are 9 of them that are essential amino acids. What this means is that the body cannot actually create these amino acids, and we need to get them from our food, which means it wouldn't be a great idea to take leucine and actually stimulate mTOR to upregulate protein synthesis in a given cell if we don't have these amino acids available in our bloodstream. The reason this could be detrimental is because we may actually kickstart the production of protein synthesis at that given cell. But the way we would get all the amino acids that we need is actually by taking amino acids out of already created muscle tissue. For example, let's say you take a leucine supplement right after a leg workout. You'll have more blood flow into your legs than into your upper body. This means more of the leucine will go to your lower body and stimulate more mTOR activity in your legs. And if leucine does actually stimulate protein synthesis to kickstart in your legs, we may actually take these amino acids from our upper body in something that we haven't used in a long time, like our rear delts or our biceps, and use those amino acids to increase the size of our legs. The only time I could actually see this being somewhat beneficial is if you are trying to reproportion your body mass so that you have larger legs and a smaller upper body, or vice versa. So once again, there's nothing wrong with taking a leucine supplement, but I think it'd be much better to get leucine from food because this will also come along with all the other amino acids we need to support protein synthesis. And now there's only so many of these mTOR molecules and only so many cells that we can stimulate. So it appears that 5 grams of leucine in a male will maximally stimulate mTOR. Additionally, about 40 grams of high-quality protein will maximally stimulate protein synthesis. So every time that we eat a meal containing protein, we would want to be looking to get about 40 grams. And now we would want to do this every 2 to 3 hours. And I know what you may be thinking. Why wouldn't we do this every hour or even every half hour in order to stimulate this process as much as possible? And the reason for this is something referred to as the muscle full effect. If we eat around 40 grams of protein, we will maximally stimulate the available mTOR and maximally stimulate protein synthesis. Once we've done that, we have no other use for these amino acids. And while amino acids are used for things like creating hormones, neurotransmitters, receptors, and digestive enzymes, the body is going to make sure that those things are already covered before we actually go to increasing our muscle mass. So typically, if the body is going to perceive that there's enough amino acids available to increase our muscle mass, it means that we've already covered our bases on the creation of hormones, neurotransmitters, and other protein structures. The best way to think about it is that the body will choose to increase our muscle mass last. So once we've maximally stimulated protein synthesis, any extra amino acids that we eat are simply going to be turned into glucose. And if we don't use that glucose will be turned into body fat. And now if you are on a carbohydrate restricted diet, it could actually be a benefit to increase your protein intake to make sure that if you are using amino acids for gluconeogenesis, they're coming from dietary protein rather than your muscles. But since we already really focused on making sure that our glycogen is supplied throughout the entire day, we likely would actually convert this extra protein into body fat eventually. And now it is important to remember that a large amount of protein, such as something like 100 grams of protein at one time, first has to be turned into glucose before it can be turned into body fat. This will actually increase our insulin levels. And now, as we've mentioned insulin already, there's nothing wrong with insulin, and there are some periods of the day where we want higher insulin in order to promote nutrient storage. However, during the periods of time where we're purposefully looking to burn body fat, increasing our insulin levels will actually inhibit the enzymes required for liberating stored body fat. So this transient increase in insulin production in response to increasing our blood glucose from gluconeogenesis of amino acids will periodically halt the release and oxidation of body fat. So there's nothing wrong with doing something like an intermittent fast where you decide not to eat until 12 o'clock. However, the first thing that I'm looking to right when I start eating is going to be protein. And if the main goal is to put on as much muscle as possible and lose as much fat as possible, I would probably do 40 grams of protein every 2 to 3 hours. And you could possibly even increase the amount of protein that you eat immediately after working out because you simply will be able to uptake more of these amino acids. And the only other note to remember is that we would probably want to diversify the different protein sources we are eating just to make sure we are getting every amino acid in a proper ratio. But as I will discuss in a moment, the meal after training and before bed that contains carbohydrates, I would actually choose a leaner cut of protein. So in these meals, I would prioritize lean tryptophan-rich protein sources like chicken breast, turkey breast, and white fish. With that being said, let's move on to dietary fat. So technically, we can store dietary fat inside of our muscles, and this is referred to as intramuscular triglycerides. And actually, one of the adaptations to exercise is increasing the amount of intramuscular triglycerides that we can store at any one time. And now with the meal structure that I mentioned earlier, we would not be in a state of ketosis because we are simply eating too much carbohydrate. However, once we have maximally filled up our glycogen stores, we really don't require much more glucose. So in the meals between your first and last meal, I would actually recommend increasing the amount of fat that you eat. And the reason for this is because fat will not drastically increase our insulin levels. And while that doesn't mean that fat can't be stored as body fat, it simply means that fat doesn't require insulin to be stored as body fat. And the benefit of this is not because insulin is bad, but because insulin will transiently inhibit us from liberating body fat from stored adipose tissue. And if we eat an abundance of fat, we are not going to be storing fat and liberating fat at the same time. However, it really just seems that the transition between storing and burning happens more efficiently and at a quicker rate. Having circulating insulin can actually inhibit us from liberating body fat for a longer period of time than if we didn't have the insulin at all. And this is simply because the body is not a perfectly timed machine and sometimes will produce a little bit more insulin than is actually required. However, in the meal that contains carbohydrates, we will have an increase in insulin. And the one thing that oftentimes we really want to avoid is increasing the amount of circulating fatty acids at the same time that we increase the amount of insulin that we have. This is because insulin is nonspecific about where it takes these macromolecules. And at the moment, the muscle tissue is uptaking an abundant amount of carbohydrates and amino acids, which will actually transiently inhibit its ability to intake fatty acids, which means that the only place for these fatty acids to be diverted to is either the liver or the adipose tissue. We don't want these fatty acids accumulating in the liver because this could lead to some negative ramifications if the liver can't keep up. This is referred to as fatty liver disease, and it is when an abundance of fat actually begins to build up inside the liver and cause liver inflammation. But more than likely, we are a healthy human being that will be able to easily divert these fatty acids directly into adipose tissue. But given our goal, this is not what we want. So we would simply want to lower our fat intake in the meals that we are ingesting carbohydrates. However, we can use the meals in between to really diversify our protein and fat sources. I would actually use these meals to choose fattier cuts of meat like steak, salmon, and eggs. Not only do these foods have an amazing amino acid profile, but they have a bunch of the nutrients that we wouldn't be getting from carbohydrates and lean protein. These include B vitamins, which are required for most of the enzymes involved in creating energy in the first place. Eggs contain an abundance of choline, which is extremely important for proper brain function as it is the precursor to acetylcholine. And now I did an entire episode about acetylcholine that I definitely think you should check out. But the more acetylcholine that we have, the better we will be able to remember and learn. Things like salmon and egg yolks also give us an abundance of vitamin D. Vitamin D is going to help with our immune system and maintaining proper calcium levels. And I'm not going to go on another biochemistry tangent, but calcium is required for every single muscle contraction, and all of the neurons inside of our brain to actually release neurotransmitters. And it has a ton of other roles in the body as well. So with that being said, I really think we have the 3 macronutrients checked off. The first meal of the day right after the workout would contain most of your carbohydrates and a lot of protein. Specifically, we would choose fast digesting fruits in order to supply our carbohydrates, and we would have a protein that is rich in tryptophan. A perfect meal would be a large fruit salad containing oranges, melon, berry, apples, and other fruits that you like, and then having something like chicken, pork, or turkey with this fruit salad. And then the meals after that, we would look for around 40 grams of protein, trying to really diversify the types of proteins we're eating, such as eating steak, salmon, and eggs, and then trying to keep whatever we eat with it lower carbohydrate. This could be something like lower carbohydrate vegetables like leafy greens, broccoli, cauliflower, Brussels sprouts, cabbage, peppers, zucchini, cucumbers, asparagus, mushrooms, green beans, anything like this. Or maybe you choose something that is even lower in carbohydrates like avocado. And we would actually prioritize this period of the day to try and lose as much body fat as possible. With that being said, just because you aren't eating carbohydrates and you're eating fat doesn't mean you're actually going to liberate stored body fat. You still can't overeat and overconsume food during this period of the day. So my only real recommendation is going to be making sure that your meals are as nutrient and protein dense as you can. And now everyone's situation is going to be different. Some people are going to be much more active and have to increase the amount of carbohydrates and fat that they're consuming. But I think this structure of having your first and last meal contain protein and carbohydrates, and having the meals in between being higher in fat and lower in carbohydrates, is a broad structure that you can use and implement your specific energy needs into. With that being said, there are just a few more things that I want to talk about. The first one is water. Keeping water intake high throughout the entire day is very important, but there are 2 times that we could actually mess around with our water intake in order to get specific effects. The first is going to be during the meals we are eating carbohydrates. If we want to store as much glycogen as possible, we're going to want to try and be as well hydrated as possible. And I can't give you specific recommendations or numbers around this, but simply trying to drink as much water as you feel comfortable with without getting distended and bloated, and making sure you're properly hydrated entering and throughout the entire workout, and throughout the entire day for that matter. However, there is one Ayurvedic principle that I want to mention about water intake, and this is actually to decrease the likelihood that we will wake up in the middle of the night to have to go to the bathroom. And this would be trying to consume 70% of your water in the first half of the day, and then trying to stop drinking water about 30 minutes before going to bed. And now some people recommend extending this longer, but I think 30 minutes is a good baseline. And now the other tip to prevent waking up and going to the bathroom at night is actually taking a small bit of sodium before bed. Sodium actually increases the production of what's called antidiuretic hormone. This will actually cause the kidneys to reabsorb water before it gets to the urine. And for a brief period of time, this could be helpful to keep us asleep and not waking up to use the restroom. And now this brings us into electrolytes. There's really no timing around sodium and potassium other than maybe that small bit of sodium before bed and trying to have as much potassium with our carbohydrates as possible. Luckily, most of the carbohydrates that we would ingest already contain potassium, so we'll be okay. And since everyone's sodium needs are different, I'm not going to give any recommendations around sodium. And if we're looking at magnesium, it does actually appear that the amount of magnesium in our food supply is going down. So we may actually want to supplement magnesium. With that being said, coffee does contain a good amount of magnesium, and it doesn't have to be caffeinated coffee. However, I have found personally that magnesium glycinate or magnesium bisglycinate is extremely helpful for my sleep. And taking magnesium bisglycinate before bed definitely increases my deep sleep. So now let's talk a little bit about caffeine and timing caffeine appropriate. So there's absolutely no need in our body for caffeine. However, it can be beneficial. So it takes about an hour for caffeine to actually be metabolized and start its effects. However, the amount of time to get caffeine out of our system varies drastically between two people. Some people are referred to as fast metabolizers, and they may clear caffeine within 2 to 4 hours. But other people are slow metabolizers, and it could take up to 24 hours to get the caffeine out of their system. So there's no specific protocol around caffeine, and my general advice would simply just to be to try and stop drinking caffeine as early in the day as possible. So taking caffeine about an hour before a workout will allow us to enter the workout when caffeine is beginning to hit in, which can give us more energy for the workout. Additionally, something that's really interesting is that it seems like caffeine can actually increase our ability to store glycogen after a workout. With that being said, I think caffeine's a bit of a double-edged sword because it will increase our output of cortisol and adrenaline, which has the potential to increase the amount of amino acids we pull from muscle tissue. However, both of these hormones also increase the amount of glycogen we turn into glucose and put into the bloodstream, and increase the amount of free fatty acids we liberate from body fat, therefore increasing our nutrient availability inside of the bloodstream. But the reason that caffeine actually impacts our sleep is because it will inhibit a specific hormone called adenosine. And adenosine has 3 specific functions that could be very helpful after a workout. So because of the high ATP use during a workout, we will actually accumulate adenosine because adenosine is a breakdown product of ATP. And apart from its function on the brain to make us feel tired, adenosine will actually decrease our blood pressure, decrease our heart rate, and actually it will act on the kidneys to allow us to reabsorb sodium and water. And because adenosine does actually seem to be local because it accumulates where the ATP use is actually occurring, we will likely have much less adenosine in the brain and much more circulating in our bloodstream, which will find its receptors on the kidneys and the heart. Therefore, the adenosine produced from exercise may not actually cause as much of a tired sensation, but it will definitely help decreasing blood pressure and heart rate, which will be elevated from working out. And my hypothesis for why caffeine has been shown to be beneficial for glycogen synthesis could potentially be a function of actually increasing the rate of gluconeogenesis that we're going through, but I'm not quite sure about that one. And now, like I said, I don't have any recommendations around caffeine because it's so individual, but I did want to throw these ideas at you so you can make the best decision for your situation. And now the very last thing I will mention in terms of nutrient timing is supplements. Specifically, I will say that certain supplements should not be taken on an empty stomach. These include fat-soluble vitamins like vitamin A, D, E, and K, because we simply cannot absorb these without the presence of dietary fat. However, some supplements can be taken on an empty stomach, and some actually show efficacy for being more digestible on an empty stomach. One specific example is zinc, and I think the reason for this is actually really interesting. So it's been found that many of the nutrients inside of specific vegetables, like phytates, actually drastically reduce the amount of zinc we are able to absorb. Zinc seems to be one specific mineral that stands out above the rest in terms of its vulnerability for other food that we are eating to inhibit its absorption. So one of my favorite studies to date is actually one that they did on oysters and zinc absorption. The control group was given 120 grams of oysters and nothing else. The other 2 groups were given 120 grams of oysters either with corn tortillas or 120 grams of oysters with black beans. The group given the oysters with corn tortillas absorbed absolutely no zinc whatsoever, and the group given the black beans only absorbed about 1/4 of the zinc as the control group did. And that's because both of these foods contain what are called phytates, which is an indigestible protein found in plants that inhibits the absorption of a lot of vitamins and minerals, such as zinc and magnesium in particular. So I would actually choose to take zinc on an empty stomach in the morning. You can also take B vitamins and vitamin A because these are water-soluble vitamins. However, the meals in between the carbohydrate meals containing an abundance of fat and protein, if you aren't eating any vegetables in these meals, and instead maybe you choose to do something like steak and eggs, then this could be a great time to take some of your fat-soluble supplements. And now I do want to mention antioxidants. These include things like vitamin C, E, and K. Antioxidants act to neutralize what are referred to as reactive oxygen species. And these are unstable molecules that are typically produced as byproducts of energy metabolism, meaning the levels of these substances is increased during exercise. And these molecules are very unstable and reactive. And without getting into too much chemistry again, the reason they are reactive is because they do not have enough electrons. So they try to steal electrons from healthy tissue like the membranes of our cells and different enzymes. And this could actually cause enzymes to become infunctional and can cause inflammation of the membranes of our cells. This is referred to as lipid peroxidation, and it's actually what occurs when you expose oils to high temperatures, which is one of the reasons that many people recommend against this. However, a healthy amount of these molecules that is produced during exercise is actually one of the most potent stimulators of protein synthesis and muscular adaptation. Antioxidants could actually neutralize these molecules, which could decrease the signal that we need to grow and repair. And in certain studies, non-steroidal anti-inflammatories and antioxidants have been shown to slightly decrease muscle protein synthesis. And while I can't say that this has any real effect, all I can say is that it could be better safe than sorry to try and put your antioxidants or anti-inflammatory supplements as far away from exercise as possible. With that being said, that is really all I wanted to touch on, and my microphone is about to die. I know this one was long, but I hope it was packed with a ton of information, and I hope you got some practical takeaways. So I want to say thank you for listening, and I hope you come back next episode. Have a great day.